So I want to start where we last left off with something circular, which was the circle lab. So in that circle lab, we determined that pi is actually a function of circumference and diameter. It's not just a number. It specifies a physical relationship, at least to the degree that we want to pretend that circles are physical or substantive things, which they're not. They're just things that we've made up to do whatever. So we have this relationship, but I want you to think a little bit differently about this. And hopefully you recall that pi is in degrees 180 degrees. So really when it comes down to it, the relation pi equals c over d is more of a half circle relation. Weird thing is that circumference is the whole circle, all the way around, and diameter is all the way across. So somehow the ratio of the entire circle perimeter and the entire circle width is half of the angle inside of the circle. Strange how that works out, but all I'm trying to do is get you to shift your thinking. All right, maybe I could improve that by, instead of thinking about diameter, I'll think about radius. And that would mean I could write it as 2 pi, the full angle on the inside, is the ratio of circumference to radius. Now, here the angle 2 pi, which is in radians, not degrees, is the entire once around all of the internal angle, nothing left out, nothing added. So it literally is, from an angular standpoint, full circle. 2 pi is literally full circle in terms of the angle. Circumference is still full circle in terms of the perimeter of the circle. Radius, while it's not half the distance, it is fundamentally full circle, because if you remember the definition of a circle, it is a collection of points, all equal distant from a central point. And guess what length is always that length? The radius. So we literally have, in this new form of our function from the circle lab, we have a full circle relation. 2 pi is circumference per radius. Now, what we could do, and I'm going to take this thing here and sort of, you might want to go down instead of up, but I went this route. I could rearrange this as radius is circumference per 2 pi. Could I not do that? I have a constant. It's a fancy form of r, okay, in this case. And for sure, we know that there's a one-to-one relationship between the circumference, the full circumference of a circle, and the full angle inside of that circumference. There's got to be a connection, okay? Well, does the connection hold if I start taking parts? So if I were to, and I'm going to rewrite this partially, what if I took a chunk of the circumference? And if I want to keep the radius constant, then I need the same chunk. Didn't I really do, I maintained the balance by dividing each component of this ratio by the same fraction, whatever n is. Well, what would be circumference, some fraction of circumference, what would we normally call that? I think I've used the word already. We'd call it an arc length, wouldn't we? And we tend to use the symbol S for arc length. And some fraction of the whole circle, what do we normally call that sort of thing? Well, what sort of thing was 2 pi to begin with? It's not an arc length, it's not a radius. What is it? 2 pi is not a circle. 2 pi is something that a circle possesses. What would some fraction of 2 pi be? It would be in, it is in radians. It's what? An angle. Wouldn't that be some angle? So this would be some arc length in and some angle in, wouldn't it? Well, hopefully you recognize that all we have here, if r equals s per theta, then I have the equation that you should recognize, s equals theta r. It is the classical definition of an arc length that you would have seen in your pre-calculus course or any trig course you might have taken. And all we did was develop it kind of from first principles. We knew what pi was as a number and what it related, the relationship that pi was, and we just thought it through and came up with the formula that you took for granted from prior coursework. So that's one way to think about it. That would be probably the closest way to what you're most familiar with to derive the formula. All right. Now, if we were to think about it in terms of the way we build laws in this course, it might go a little bit differently. And what we could do is have our thing here, and if we pretend, let's pretend that we don't know anything about arc length, or that there's such thing as an angle. We just know I have this circular thing, and I'm calling pieces of the circumference arc length because they're archy and they're long, right? Sorry for the high-tech terminology. And we know that there's always the same distance from the middle of the circle to the ends of my arc length. All right? And no matter what I do, if I have another arc length down here that's longer, I keep getting r. So I notice that every arc length seems to have something, there's always something associated with it. All right? But the radius never, ever changes. So what I could say is I know that arc length is dependent on something, right? What would happen to arc length if I made r longer? Would arc length get bigger or smaller if I made radius bigger? It would get bigger, and if I made radius smaller, it would get smaller. But the radii, they could just be line segments in space. They don't have to be part of a circle. All right? But they're always the same. They don't change. So things that don't change are constant, and they tend to be independent of the things that do change. So I could know, hey, S is dependent and R is independent, which is, if you remember from the few laws we made, once you determine what the dependent thing is, the next thing in the trick box is to make a fancy formula one out of the thing that's independent. Okay, we just did that. And I know that in some way arc length depends on radius, so I put it in the laws and code, axioms and code for what laws describe. And so we have this relationship here, S per R. And so we could say, you know what, as S gets bigger, the space beneath it that subtends it, you might remember that lingo, gets bigger. And as S gets smaller, the space beneath it gets smaller. So there's something, this space here, and if we wanted to, we could say, you know what if I call that thing angle, and I'll call it theta, because theta is the obvious choice for the thing called angle. Just nod. Say, yeah, obviously, theta. Of course. What else would you call an angle? Why call it angle? Just call it theta, because that makes more sense to call it theta. All right. It's a symbol. So here, what do we have? We have S equals theta R. So pretending we didn't know what an angle was, et cetera, we could construct the idea using the lawmaking thing, which is fundamentally the same as what we just did on the previous screen, but a different way nonetheless. They're consistent with one another. I would say they're equally good. I sort of like the other one a little bit better, even though the lawmaking scheme I'm half responsible for, me and my collaborator. But it's more straightforward, but only because of your prior knowledge. All right, so it's important to know that distinction. So we have this uh, bit here, and one of the things that we can uh, bank on here in our lawmaking, we can say every arc length requires uh, an angle. That's essentially a law. Every arc length requires an angle, right? So we could, that's what we have. Whoops, that's not what I want to do. Uh, so that's what we have right here. Every arc length requires an angle. And the radius is the glue that's holding that together. It's the one thing that's constant, all right? Now, arc lengths are distances traveled, correct? What does a distance traveled always require? It takes time to change your position. And I can look at, this is position A, that's position B, this could be position C. It always takes time to go from one position to another, and in this case, our change in position is along an arc length. So the displacement would still be the straight line vector, but the distance would be the arc length. But it doesn't really matter. It always takes time to change that position, regardless of how that position, the path. Okay? Change in position always requires a change in time, irrespective of the actual path, whether it's straight line or wiggly line. All right? Also, we're used to delta S as a general change in position, and now S is going to be an arc length, a particularly curvy kind of change in position. All right, so the other choice was to use R, which is another conventional symbol for a change in position, but we have big R for radius, so there's no way to escape some sort of irritating symbol confusion in circular motion because of just the nature of the way we've developed those things. So if I were to, every arc length requires an angle, or I should say every change in arc length requires an angle. So if I have S equals theta r, every change in arc length would require a change in angle. But as we just said, and both require a change in time. Now, I could multiply one side by a fancy formula 1 of delta t per delta t, or I could just know if there's a law specifying that this always requires that, I can know that I need to write it as a this per that. So delta s per delta t is a this per that. Delta theta is another this for the same that. Well, what's delta s per delta t according to the first zeroth law? Isn't it speed? It's a linear speed, isn't it? Change in position from A to B. All right. So if the angle's small enough, there's no difference between the arc length and the displacement. Here's the new thing that will be hopefully remotely familiar, but you're probably not as familiar as I'd like you to be. We'll find out. Delta theta. That is an angular displacement, meaning you sweep out some number of degrees or radians. It's an angular displacement. It's a roundy displacement. Okay? So if I have an angular displacement per unit time, what is that ratio? If a linear displacement per unit time was speed, linear speed, then an angular displacement per unit time would be an angular speed. And the obvious choice for symbolizing angular speed is the Greek letter omega in its lowercase form. You knew that, right? Of course. Of course I would choose a really curvy W in another language to symbolize angular velocity because there's so many W's in the English word angular velocity. I just work here. I can't control the symbols here. But the interesting thing about this equation is it relates a linear speed to an angular speed. All right? So V would be, a speed going off the circle like that. I could use, that'd be our V, whereas omega would be a roundy speed. In fact, I have a t-shirt I've worn a couple of times like, this is the way I roll. It's got an omega in it and a V. The omega's on the inside track of round angular displacement per time motion, whereas any point on the edge would have a velocity that's tangent to the path at that moment. All right. Little oops here. This isn't WT. This needs to be R. Sorry about that. There we go. But I think you realize that if you have a speed, if V equals omega R, isn't it the case that every Can't V change? Couldn't V or omega change? So every change in speed requires a change in time. And in fact, in this case, we have two kinds of speed. We have a linear speed and an angular speed. They're both speeds, and I don't care what speed it is. If it changes, it takes time to change that speed, just like it does to change the position. So every, whoops, every change in speed, so there's change in speed, requires a change in time. Well, what's delta V for delta T? Second zeroth law, that's acceleration. And a change in angular speed per unit time would be an angular acceleration. So we have another linear to angular conversion. You can just angular speed would be the ratio of the acceleration in the linear direction relative to r, etc. So we have another two equations here. And we'll leave the changes at that because we didn't take the other acceleration to another level, at least not yet. So I have these two equations. Uh, acceleration is alpha r, and velocity is omega r. Two basic equations of circular motion in addition to the fact that s equals theta r. Right, so if we wanted to have our three basic equations for circular motion, those are part of it. Now, I want to address something a little different. Let's change up colors here just because we can. So we have the linear world. Since we've been talking about linear to angular, and you'll find this in pretty much every physics textbook in the galaxy. So in the linear world, if I had something like delta S equals V delta T, over in the angular world, I would have, instead of linear displacement, I'd have angular displacement. And instead of linear speed, I'd have angular speed, but I'd still have time. So it's really the named variables and their appropriate symbols. And then, of course, this thing would bust out into, say, S equals S naught plus V delta T. This would be a final theta is an initial theta plus omega delta T. All right. V is delta S per delta T, omega delta theta per delta T. So just these natural conversions in language. And then you also have delta V equals A delta T in the linear world. So in the angular world, you have a change in angular velocity equals an angular acceleration times time. And then the same business. V is V naught plus A delta T. A is delta V per delta T. Omega is omega naught plus alpha delta T. Alpha is delta omega per delta T. So it's the same structure. So solving problems dealing with circular motion, same business. If we had this equation where the final position is the initial plus V naught delta T plus half acceleration delta T squared. Well, theta would be theta initial. Those are, instead of linear positions, I'd have an angular position. Instead of a linear speed and time, it would be an angular speed and time. And instead of a linear acceleration, it would be an angular acceleration and delta T squared. So these worlds have the same structure in terms of how these quantities relate to one another, even though One world is straighty straighty, and the other world's roundy roundy. All right? But the way that those things add up, quite literally, is the same fundamental structure. All right? Just a change in variables. So that's your equation list, which will be readily available everywhere you can look uh, for that. And one last bit of news here to develop our last equation. So, given a circle that has some radius, it's pretty lousy radius here, and we'll call this some angle theta. And let's say that this is point A and this is point B. And let's say that motion is from A to B. And so there's some angular speed that the object takes. And so it could be a circular path where an object is free to not go circular, but it's going to in this case, or this could be a spinning disk, and A and B are positions adjacent to the disk, and there's a peg there and it's just moving. There's a lot of ways to think of this, okay? And so at some point in time, there's a linear speed, VA, tangent to the path. And then at some other time, there's an identical speed, but I'll call it VB. By the way, these speeds have to be the same if it's circular motion, or assuming a constant angular speed. Obviously, if it's speeding up, we'd have a non-zero acceleration. So this is assuming, so if acceleration is zero, then VA equals VB. We could just say that's V. All right? That'll be important later. So a question to ask is, what is delta V? Well, if it's constant speed, you're going to know it's zero, but let's go ahead and work this out. And we're going to work this out graphically. So a simple answer, a non-numeric answer to what is delta V would be to just write out what everybody knows symbolically it would be. And then you'd say to yourself, I think it's going to be important to use graphical addition of vectors, okay? Because this would be a boring thing under constant speed, because the linear speeds would be the same if the angular speeds are the same and the radius doesn't change. So it'd be really boring. It can't be this boring. Surely the professor wouldn't trick us that way. That's almost always true. So if I'm going to do vector addition, it will help to rethink subtraction, since it doesn't actually exist in the field axioms of arithmetic, as the adding of a negative. So if I take VB, which was shown to be this is VB, and I take VA and turn it around, instead of it going up, it goes down. That would be negative VA, and I add it tail to tip, because that's how you do graphical addition of vectors. Then I get this. That would be VA. And the sum is delta V, which is always drawn from the tail of the first one to the tip of the last one. So guess what we have? Well, acceleration is always that's the main event, the change in speed, that's the main event in acceleration. If you know the direction of the change in speed, you know the direction of acceleration. So guess what happens? Acceleration is always center seeking. It wouldn't matter where we rotated positions A and B, or whether we squeezed theta to be smaller, the acceleration will always be towards the center of the circle for circular motion. You'll have a constant speed tangent to the circle. You'll have a constant angular speed inside of the circle, but the acceleration vector, or the change in speed vector, will constantly be changing its direction. And that's one of the fundamental things about a vector. It has magnitude and direction. So you could maintain a constant speed part of your vector, but have a constantly changing direction to your vector. All right? So if you're on your skateboard going at a constant speed and I push you and you don't fall off, you're still going that speed, but you're going a new direction. Okay? If you're on a curve and you're on cruise control, surely you've done this. Did you change the car's speed? You didn't accelerate on the accelerator, but by changing the direction of the car, you did accelerate the car. You accelerated it towards the center of some circular path that you don't see. And that's the idea here, is if any motion could have a circle, any portion of a circle fit the path. So you turn on a curve, like exiting exiting a freeway or entering a freeway or whatever. If you're on if any part of that path, a circle would fit it, then for that part of the path, all of these rules apply. As soon as it's no longer a circular path, then these rules stop applying and you're into linear motion again. So you could be on a curve that's circular motion, go straight, linear, go on another curve, that part's circular motion, et cetera, et cetera. You're in and out of circular motion. So we have a center-seeking acceleration. Now, also theta is right here inside of this triangle. So as theta goes to 0, my arc length, or my change in arc length, goes to just the path, the displacement. All right. So what this gives us, and I'm going to simulate small angles here. And every textbook in the universe also does this. This is a standard treatment. I have these two similar triangles. The way that the changing speed relates to the speeds has the same angle as the way that the changing arc length relates to the radius. And so when I have similar triangles, that allows me to write delta S per R equals delta V per V. But delta S, since it's heading towards a straight line, I can write as V delta T, which means I can write V squared per R equals delta V per delta T, which is acceleration. You just get that by, if I multiply both sides by delta V, divide both sides by delta T, and so we come up with, and I'm going to have to scooch things up here into a free spot. You don't have to do this, but I'm going to create a new little space here. So I have acceleration equals v squared over r. And this is centripetal acceleration, not centrifugal, but centripetal acceleration, meaning center seeking. All right, center seeking acceleration. Also, if you put, instead of v for the v squared part, if you put omega r in there like we found earlier, then centripetal acceleration just becomes omega squared r. I trust that you can see how the r's cancel. All right, omega squared over r would be omega squared r. And so we have our fourth equation, if you will, that comes from a vector analysis of circular motion. All right.